28th is going to be a wild night. The 28th is going to be a wild night. No, we'll do it over break. I just hate having a son. That's so much things I have. It's like, so I think it's really easy though. How do you have like 6 things due Friday? Like,
Okay,
like
so, morning everyone. Okay, let's get started. Okay, quickly, spring break's coming up. I didn't want you guys to be stressed at the end of this week, so I do want to keep us going with weekly problem sets. So the resolution of that is to have both of the next 2 problem sets due on March 29th, which is 2.5 weeks away. Okay. And I hope, compared to the last problem set, which I know is a bit challenging, the next 2 are going to be easy. Okay? All right. Particularly problem set 7, I think. All right. I have a bunch of things going on this afternoon, so I can't make my regular office hour today, but I will be in tomorrow on the usual schedule. And then lastly, I have a couple of spots open for lunch this Thursday. It's the one of the 3 that wasn't fully signed up for. So if anyone is interested, let me know after class, okay? So that's lunch on Thursday from 1 until 2 p.m. Okay, so we're going to continue our discussion of capacitors. And we'll talk a little bit about determining capacitance based on geometrical or physical properties. That's where we ended up last time. A comment to say about that. Then we're going to look at the important problem of how to look at setups that have multiple capacitors ganged together in some way and see how we will handle those. We often find that it's both useful and not too difficult to simplify let me call them circuits, since we're starting to talk about circuits that have multiple capacitors, so we're going to explore how to do that. A couple of worked examples, which now most of you have written this down. I'm going to get rid of them so they're not too distracting. Then we will talk a little bit more about the energy that we can store in the electric field associated with capacitors, and then as time permits, we're going to continue and look at how we can modify the simple capacitors we started out with, which either have vacuum or air, which actually behaves in this context very much like vacuum. We're going to add some richness to our lives by putting in some specific insulating materials in the gaps between capacitor plates and see what that buys us. So that's the roadmap for this morning. So, as we left off on Thursday, there was a tremendous amount of confusion, mostly instigated by me, about signs and potential differences. And I have to say, having been working through a bit of this over the weekend and thinking about it, I'm inclined to want to rewrite a couple of pages of my notes to make it just as simple as it possibly can be. So the footnote here, I think, is that in the case that we were looking at, and you'll remember it was this sort of nested spherical objects problem, is the way we treat the direction of the electric field and the radial vector. And I had some nice input from at least one of you on this over the weekend, which was helpful. But I still want to try and make it as crisp as I possibly can. So stay tuned for that. I'm going to try and just put up less than a page of notes to make this straightforward. Bottom line, if you're confused at all, think about this. The potential should decrease if you're following lines of electric field. Okay? The electric potential should decrease if you're going in the direction of electric field vectors And conversely, the potential should increase if you're going against the direction of electric field vectors. So think of that as potential getting bigger as you go towards positive charge, and in a sense it's getting smaller or less as you go towards negative charge. Okay? So again, I hope to sort of clarify this sign confusion, and I'll try and get that up between now and Thursday. But when you're getting confused with all those possible sign changes that come in when we do our delta E calculations, just at the end of it, check that your potential is decreasing as you go in the direction of electric field lines. Joseph?
You depend on the sign of the charge that's at any given point.
Yeah, but remember that's essentially what defines the electric field for us, right? So electric field, of course, originates on charge, and so the more universal way of thinking about this is in terms of the electric field. Yes, it's very much tied up with the charge. Okay, so let's jump in and see how far we get. And I want to have you guys work a couple of examples, one of which is a relatively easy warm-up one, and the second is much more complex, the more representative of sort of multi-step problem that you might see on a homework or on a test. So let me just, because we were rushed at the end of Thursday, I want to go back and just quickly remind you of the calculation of the capacitance associated with a parallel plate capacitor. And so we're aiming here for an expression that's in terms of the physical properties of the parallel plate capacitor. So calculating C for specific physical realizations of capacitors. And you hear me occasionally using the phrase caps for shorthand for capacitors, so hopefully you're comfortable with that. All right, so what's our strategy here? Generally, and again, this is just a reprise of what we had on the end of Thursday's class. We're going to assume plus Q minus Q on the plates of the cap, regardless of what geometry it is. We'll calculate, if we don't already know, the E field in the gap based on Gauss. We'll calculate the potential difference. And remember what I said on Thursday, if any of you were not here, bears saying again. My convention, which I only realized after the fact is different than the textbook, is to define a potential change as I go along the path in the electric field as being the negative of the path integral from your starting point initial to ending point final of this. And so in this case, V delta V is defined as it usually would be, which is V final minus V initial. Okay? So our textbook has the unusual choice of actually keeping this positive and switching the direction of these two, which frankly I wouldn't recommend, but at this point, whatever works best for you. And then we're going to finally calculate capacitance just by looking at Q over V based on our original definition. Okay? So that's our standard strategy. Let me just remind you again, repeating what we did last time. So the parallel plate, more standard geometry by far. And you'll notice that I'm drawing these plates as being rather thick to really emphasize the fact that they are indeed rather thick. And in particular to emphasize the fact that, let's say, if I have positive charge on the left plate and negative charge on the right plate, that charge is going to tend to be on the innermost surfaces, okay? So we expect that just based on Coulomb attraction. And this is different from when we have these plates that are isolated. If I only have this one, I expect equal distribution of the charges on both faces, inside and outside. But as soon as I bring a second plate in with opposite charge, I expect all of the charge to migrate to the inner surfaces, okay? So I wanted to really make that clear with these thick plates as shown there. So we have plus Q on this guy, negative Q on this guy, and as expected, we're going to have, to some approximation, a uniform electric field in space and time. Okay? Now, I mentioned on Thursday in those closing rush minutes a couple of things about what happens elsewhere. First off, the reality that the electric field is not totally uniform, and as you get to the ends of these plates, we're going to expect a little bit of flaring, something like this. But we should also expect on this side, since there's no charge here, there's no field here, no field here. And so what we're about to do when we figure out the electric field in this circumstance is define a Gaussian surface that encloses all of the charge on one of the plates, in this case the positive one, and it goes down through the middle of the left-hand plate here. So it's in the bulk of that conducting material, so the electric field in this region is 0, okay? So we've chosen this specifically for that reason. Let me make a note of this. So E is 0, careful here, on the outside, on this part here. And up here we're going to claim that in these sort of fringe regions that E is negligible. Okay, so somewhat of an idealization. All of this to say that we're only going to treat there being finite electric field passing through this region on the right side. All right, so let's see what else do I need on here. I'm going to say that the area of these plates is just A, doesn't matter what the shape is, let's just keep it as A. All right, so there's step 1, putting the charge, plus Q, minus Q on the plates, calculating the electric field in the gap. So what do we have? We can use Gauss's law here. Maybe I'll have you guys help me out with this a little bit. Under the simplifications that I just described, if I'm trying to figure out the total electric flux passing through this green hashed surface, and this is uniform, so you can imagine these plates kind of extending like this, what's the total flux passing through that green hashed surface? No.
Is it E?
That's the field. What about flux?
Oh, the flux.
You're halfway there. Yep. EA. Right?
Okay.
So I have this set up in such a way that we're assuming the electric field is left to right, uniform. This surface is set up so the area vector is always parallel to the electric field. So our scale product becomes simple. The electric field is uniform. The area is just what it is. This just becomes EA. No contribution from the ends. I'm claiming it's negligible here. And there's no contribution from this side because they've drawn the left side of this surface within the bulk of the conductor. We know the electric field there is 0. So that's that. In terms of the total enclosed charge, it's just Q in this case, divided by epsilon 0. So in this case, I get that E equals Q over epsilon A. Okay, so there's that. Now let's go on and do step 3, which is to figure out delta V. And in principle, as you heard me say last time, we're still talking about delta V, so it's definitely differences in potential. But when it comes to talking about capacitors, we tend to get notationally lazy, and we often forget the delta here. So you're going to start seeing just V as opposed to delta V. Try to keep in mind it's always a potential difference from one plate to the other. And so what I can do here is I can go from, okay, I can go whichever direction I want here, but what I'm going to do is go from negative to positive. Okay, so here's a place where signs come in. I'm going from negative to positive in this case. This is not a problem that has radial R dependence in here. So I'm going in this sense against the electric field. So this becomes minus, from minus to plus, of minus E dx. Okay, so my scalar product by choice of going against the electric field here becomes minus 1. And so then this just becomes the integral of E ds. And this is going, let's say, from one side to the other. I forgot to put a separation on here. Let's say that these are separated by a distance d. So this is going from 0 to d, and this just becomes the electric field times the distance traversed from one plate to the other. Okay? So now I've got the delta V, I've got this ingredient, I know the Q, I can just go to the last step and find what the capacitance is by dividing one by the other. I apologize for running out of board space here, but now this is just C equals Q over, again, I'll keep on doing this for a little while, delta V, but then I'll stop doing it completely. And this should now become Q over epsilon A, that's this, divided by this. And if you allow me to write it like this and clean it up, eventually I get this expression for the capacitance. Okay? So standard strategy, charge on the plates, if we don't know it, figure out the electric field, then figure out the potential difference going from one plate to the other, divide one by the other, and we've got the capacitance. Okay? Now, as I said, I want to make this a little crisper in terms of a set of guidelines for you to follow the work in any case. There's no particular reason why we need to go from negative to positive here. I could, of course, go from positive to negative and calculate it this way, and so it's up to you. If you're unsure of the result, make sure that you figure out that you've got the higher potential on the side on which the electric field begins, and the potential is decreasing as it goes to lower electric field. So the potential is decreasing in the direction of the electric field vectors. All right. So the result that's of interest to us in this case is this. So instead of having a generic expression for capacitance that just knows nothing about the actual physical setup, now we've got one that knows very much about the physical setup. It's proportional to the cross-sectional area. It's inversely proportional to the separation between the plates. Okay? So that's the first one we did last time. I want to go on and just give you the outline of how this might look for a cylindrical geometry. Fairly common. In fact, the big device you saw at demonstration in class last time was cylindrical geometry. You might remember it looked kind of like a big soda can. So that's very much a cylindrical plate geometry. We can also have spherical plate geometry capacitors, much less common because they're a little bit harder to build and work with. So these two are kind of the standard geometries in practice. So what might this look like? Well, let me give you an example of something that looks a little bit like this, so-called coaxial cable. Used all over the place for various reasons, but in a lot of devices you might have around your dorm or your home. So let's look at what this might look like. So we're looking now at a slice through a piece of cylindrical plate capacitor. Okay, I didn't draw this so well, but there it is. So this is a slice. Imagine this is a cylindrical geometry that's going into and out of the plane of the board. And I want to try and put a few things on here in as clear a way as I can. So let's say I have plus Q on the interior. This is a solid cylinder going into and out of the plane of the board. On the outer cylindrical shell, if you will, a real cylinder, I have negative Q, bless you. And I'm going to say that I have, let me add some color here to try and keep this distinct. I'm going to have this be a radius A, and this be a radius B. Okay. I'm going to say that the whole cylinder has a length in that direction of, let's call it big L. So L is into and out of the plane of the chalkboard here. All right, so I've done step one. I've assumed plus minus Q on the plates. Again, these are conducting materials, so the charge is distributed on the sort of facing plates, the plates that face each other. It's on the outer surface of this, and it's on the inner surface of this. So that's step one. Now I will take a Gaussian surface that is in the region where we have electric field, and we already know what direction the electric field is going in. It is radially outwards. Okay, so we're going to follow a radial path because that makes our scalar product more tractable. We're going to do this and see what this gives us. So let me give this one a radius r. And that's now the radius of our Gaussian surface. I'm going to make it also of length L. So think of this now as a cylinder, length L in this direction, radius little r. It's sealed at the ends, as all of our Gaussian surfaces must be. And we're going to assume at the ends, I'm not going to write this up, but very much the same thing we had on here, that the edge effects are negligible. Okay? So we're not going to worry about the real contribution to the electric field that penetrates through the end caps. We're going to say it's small, and we're going to ignore it. So that's our idealization. So what do we get in that case? So let's see if I can do this somewhat equivalently. I'm going to skip at least a bit of the detail here. All right, so I want you to give me some guidance here again on what is the total flux passing through the Gaussian surface that I've defined, okay? Radius little r, it's a cylinder, comes out or goes in that way, doesn't matter which, has a total length L. That's where I'm cutting off my Gaussian surface. I'm assuming no flux through the end caps with an approximation. So what does that tell me in terms of the total flux through that Gaussian surface? That's somebody new. Another volunteer? Yes.
2 pi r L at times, like, yeah, so that's your
Okay, so E at some radial distance r times 2 pi r times L. I like that. Okay, this is the surface area of that curved part of the cylinder. Okay, so circumference of this circle, obviously 2 pi r, the whole thing has a length r, so the curved surface of the cylinder has area 2 pi r L. If the electric field, which is fixed at a given r value, is going radially outwards, so a scalar product of these two is 1. This gives me now the total flux passing through this, and I'm ignoring the end caps where I'm claiming there's negligible flux. Okay, so indeed that's that. And let's say this is just now the total enclosed charge. I'm going to come back to that in maybe just a moment, divided by epsilon. So this tells me, let's see if I can do this analogously to that, that I have ER equals Q enclosed over 2 pi epsilon RL. Okay, so that's now my electric field. We've done this calculation before, but just good to do it again, make sure you're comfortable with it. What we see now is a charge per unit length. So the total charge within that cylinder of length L, the length obviously of this thing. You might often see this actually replaced with what's effectively a linear charge density. Okay, I haven't mentioned this in passing before, but now's a good time to. Linear charge density. We're used to thinking of this as just being along a line that really has no extent perpendicular to the direction of the line. But if you think about it, I can certainly define an amount of charge per unit length, even for something that's finite size, finite radius as this is. So this is a sort of pseudo charge per unit length, but over actually a sort of fully three-dimensional object. All right, so probably that seems fine. Now, as usual, we've got our delta V equals our integral of E dot ds, and this one does have a radial dependence in it. And again, we can choose which direction we go in here, and this is the thing I'm going to try and write out in a crisper way. Posting some notes between now and Thursday. But if I happen to go from the negative plate to the positive plate, maybe I'm going like this, but I can go in the other direction. And so I need to go, for example, in this case, from R equals B to R equals A. Okay, so ds in this case is going to be a radial vector, because we're going along the radius. And the thing that I think I'm convinced by now, thanks in part to input from Jesse, but I'm still not 100% sure yet, is that by virtue of going from a point that starts out at a larger radial distance and ends up at a smaller one, we actually have built in the direction of dr in here, so I don't need to take account of it twice. So let's put this in, and so I'm going to put this into here. And when I do this, I eventually get, and there's a little bit of manipulation here, we will find eventually that delta V equals Q over 2 pi epsilon 0 L times the logarithm of V over A. Because of course when I integrate a 1 over R term, I get a logarithmic term, and then I'm putting in my values here. Yeah?
Why is it
Oh, thank you. Thank you very much. Yes. So my bad again, getting my negatives all messed up. Okay. So look at this, and again I'm going to try and write something up that makes this plausible. But I've already built in the direction of E with respect to R by virtue of doing this. Where do we expect the higher potential to be in this case? So we figured out what the magnitude of the potential difference is. Remember what I said in my introductory comments. We expect that the potential to decrease in the direction of the electric field line. So where are we at higher potential in this geometry? If I'm looking at how the potential changes across the gap. Right. Okay. So again, when signs become confusing, just step back and ask yourself what direction is the electric field, and therefore where do I expect the potential to be higher? And in this case, we expect the potential to be higher at the inside and decreasing as we go to the outside. Okay. All right. Yeah.
Just one sure I have the geometry. The inside is a solid cylinder and then it's surrounded by a cylindrical shell.
Yes. And then the gap in the middle. Yeah. Okay, so that's step 3, and then step 4, as we've seen here, is just to divide the one by the other. At this point, I may be forgetting the deltas entirely, and so this should turn out to be Q over Q 2 pi epsilon L logarithm of B over A, something like this. And so it just becomes 2 pi epsilon L over logarithm of B over A, something like that. Okay? All right, so standard procedure this time for the cylindrical geometry. I'm not going to go over the spherical case. There's a little bit in my notes about that, and there's probably also a little bit in our text. Yeah.
How come you picked up the standard side of going parallel plates?
Yeah, so why in this case and why not in that case? So in this case, because the R dependence, it's dependent on R, and then I'm putting in some specific R values where I start out at larger R and I end up at smaller R. So in that sense, I already have built it in because of the R dependence in the electric field case. I don't have any distance dependence here, it's constant. And so in that case, I really do need to put it in explicitly in this case. So again, I want to try and firm this up in a way that's totally clear and direct. And I think I'm possibly inclined to move away from the convention of going from the negative to the positive, just because it adds yet another minus sign, which is not helpful when we've got maybe 2 or 3 others to worry about.
So in the cylindrical case, you can't convert it as scalar version, is what you're saying. Whereas with the parallel plate,
What do you mean by scalar?
I mean, you have the, in the interval, you have EDS, that's just like the negative EDS, that's all.
Yeah, in this case, I'm keeping it as just EDR, but it's
Yeah.
positive, okay? But I'm going from a larger R value to a smaller R value, so that builds in for me some directional sense in this, okay? And I don't have that in this case, because it doesn't have a dependence on the variable that comes into the scale product. So that's where the